So let's consider this function here, something like this. And let's see, so we want intervals of increase and decrease. Well, I'll find the derivative. I'll always find the derivative. So I have 3x squared minus 12x plus 15. And you set your derivative equal to 0 to find the critical numbers. I see that I can divide all these by 3. And so I shall do that, equals 0. Quadratic equation, we can solve this different ways. I would factor this if I could, but I cannot factor this using integers. So I'm gonna hit it with a quadratic formula. So I have x equals the additive inverse of b plus or minus the square root of b squared minus 4ac, because that is a, all over 2a. So this equals 4 plus or minus the square root of 16 minus 20 is negative 4. This equation has no real solution because the discriminant is negative. So what this is saying is that the derivative, f prime, is never 0 because there's no real solution. Since this derivative has since this derivative is never 0, that means the original function, it never flattens out. Like the original function's cubed, it's a cubic function, it's a degree 3. Very often, degree 3s look like this, where you have sort of a flat point there, and you have a flat point there. In these instances, this cubic function would have had a couple of points where the derivative was 0, but ours is never 0, which indicates that this cubic function is probably something that looks like this, where it might have an inflection point, but it never sort of decreases. So for something like this, I'd say that the increase intervals are from negative infinity to infinity, and the decrease intervals are sort of not applicable. Let's see, what about the critical points? Because here the derivative is never 0, and it's never undefined, so there are no, we say that function f has no critical points. We say that function f is increasing on its domain, and we say function f is never decreasing. What else? Because the function never goes from up to down or down to up, these would be called like a local max and a local min. This function never has it because it looks something like this. So I'd say that function f has no extremum, no relative max, no relative min. As far as concavity, for concavity, we need the second derivative. So let's compute that here now. So the second derivative would be the derivative of the first derivative, which would be 6x minus 12. And we set the second derivative equal to 0. X is 2. Make a number line for f double prime at 2. Test points would be something like 0 and 3. Plug in 0 into the second derivative. If I plug in 0, it would be negative 12, so this is a negative number. Plug in 3 into the second derivative. That would be 18. That'd be positive. So I have negative, which means concave down, and I have positive, which means concave up, where of course concave down and concave up refer to the concavity of the original. So I'd say that the original function is concave up from 2 to forever. And I'd say that function f is concave down from negative infinity all the way up to 2. And that is an agreement with a sketch that looks like this. By the way, I knew that this cubic function had this orientation instead of this because the leading coefficient one was positive. So it doesn't look like a negative orientation. It looks like a positive orientation where, if that's the inflection point, where on this half, it's sort of concave down from negative infinity to 2. And for the rest of its life, it's sort of concave up from 2 to the right forever.